Hi, we're going to focus on calculating concentrations. During this video, we're going to look at the equations that are most common in the use of calculating the units of concentration. So during this video, you want to make sure that you record these and you understand them. You should also be able to calculate the concentration of solutions once you're done with this video and to convert between the different units of concentration. To make this session effective, you should have the class outline, the periodic table handy, and a calculator. On this slide, you can see all of the concentrations that we're going to be using. You're familiar with two of these, molarity, which is moles of solids over liters of solution. If you recall Gen Chem 1, you used this when you did titrations. The other equation that you've seen from this slide are the moles of solute. You used this when you worked with the gas laws and you were trying to find the partial pressure of a gas using Dalton's law. Now, with molarity, moles of solute over liters of solution, this is very useful because by just measuring the volume, we'd be able to calculate the moles of the solute when we deliver it. The problem that you have with this equation is that volume is temperature dependent. So if the temperature fluctuates, you would not have as good a control of the moles that you want to deliver. Because of that, in a situation that the temperature can fluctuate, it's better to use molality. In molality, notice the symbol, lowercase m. You're calculating the moles of the solute divided by the kilograms of solvent. Let's pause here for a moment. You've got two different things in the denominator. For molarity, you have solution, and for molality, you have solvent. So let's define what the solution is. The solution equals the solvent plus the solute. When we're working with molarity, you're only focusing on the kilograms of the solvent. Now in mole fraction, which we give it the symbol of an italicized X, you're using the moles of solute divided by the total moles of the solution. In that case, you would be focusing on moles and adding the moles of the solvent plus the moles of the solute. And the last equation is mass percentage of solute. In this equation, we're focusing on masses. And we take the mass of the solute and we divide it by the total mass of the solution. If we multiply that by 100, then we get mass percent. But notice the star. We could in fact multiply it by 1,000,000, and that would give us parts per million, or we could multiply that fraction by 10 to the 9, which would give us parts per billion. We tend to use these two last multiplications when we're working with extremely dilute solutions. So let's apply these. Let's do this first exercise. What is the mass percent concentration of a saline solution prepared by dissolving 1 mole of sodium chloride in 1 liter of water? At this point, you should pause the video and solve this problem on your own. And once you're done, start the video again to see if your answer agrees with mine. The equation for percent by mass is the mass of the solute, which in this case the solute is sodium chloride, divided by the mass total of the solution, which would be the mass of sodium chloride plus the mass of water, multiplied by 100. Sometimes it can be confusing to know which is the solute, which is the solvent. Remember that the solute is the one that you have the least of, whereas the solvent is the one that you have the most of. And when you look at the mixture, what you observe are the physical characteristics of the solvent. For example, you know that sodium chloride is table salt. If you add a teaspoon of table salt into a beaker filled with water, the sodium chloride is going to dissolve in it, and you wouldn't even be able to tell that you had a solution. It would all look like pure water until, of course, you tasted it. So continuing with this problem, first we need to find the mass of sodium chloride. To do this, we need to use the molar mass of sodium chloride to relate grams and moles. And that relationship comes from the periodic table. Sodium weighs 22.99 grams per mole, and chloride weighs 35.45 grams per mole. We add those two together. For a total of 58.44 grams over moles. So our moles cancel. And we've got a mass of 58.44 grams for sodium chloride. Notice the significant figures. We have 3 sig figs, so we should mark this mass with 3 significant figures. But you don't want to round it until the end. Now we need to find the mass of water. In this case, we're given volume of water. The relationship between mass and volume is the density. And I happen to know what the density of water is. The density of water is 1.00 grams per every 1 milliliter. Before I can use that conversion factor, I need to have my volumes in the same unit. So I need to convert my liters to milliliters. Remember that 1 liter equals 1,000 milliliters. We only have 3 significant figures, so we want to mark that. Rounding the final answer up to the correct number of significant figures, we would have 5.52%. How'd you do? Did you get it correct? Let's try another one. One that's a little more complicated. We're looking for given the density of 25.0% by mass of a solution of sulfuric acid in water, the density of it is 1.1783 grams per milliliter at 25 degrees Celsius. For this information, we need to calculate the molarity, the molality, and the mole fraction. There's a couple of steps that help in setting these problems up. General approach. Open up derived units. A derived unit is any unit that we substitute a word or symbol for a calculation that contains more than one unit. For example, density. Density is a derived unit. It's calculated by dividing the mass in grams over the volume in milliliters. So in this problem, we have a few derived units. Here we have a derived unit. Here we have a derived unit. The temperature, if you look at any of the equations that we use, temperature is not part of it. The reason they give us the temperature is that density is temperature dependent. And so it's just an extra piece of information that we're not going to actually use it for any calculation. So opening up our derived units, we would see that 25.0% of sulfuric acid would mean that we have, for every 100 grams, we have 25 grams of sulfuric acid in a total of 100 grams of the solution, which would be 25 grams of sulfuric acid plus 25 grams of water times 100. The other derived unit that we have is the density. We're given that 1.1783 grams of solution is the mass of 1 milliliter of solution. And this is an important step because we need to know what belongs to what. We have three things. We have grams, we have milliliters, and we have solute, we have solvent, and we have solution. So we need to know each of these and identify them properly. Notice the other thing that I did here. I took the liberty of adding 4 zeros to the milliliters, and the reason I did that is that the density has 5 significant figures. The density was calculated by taking mass and divided by milliliters, so the volume also had to at least have had 5 significant figures. So now let's start working out each of these separately. Don't forget that molarity is moles of solute, which in this case are solute of sulfuric acid, divided by the liters of the solution. Now, going back to our previous information, we can see that 1.1783 grams of solution is the mass of 1 milliliter, so we're close. But of this solution, only 25% of it is the mass of sulfuric acid. So let's determine the grams of sulfuric acid. First, let's focus on the top term, moles of sulfuric acid. And we're carrying 3 significant figures. The reason we're carrying 3 is that this has 3 sig figs. I'm not very sure why I wrote that X there. That doesn't belong. Now that we know the mass of sulfuric acid, we can calculate its moles. Need to find the molar mass from the periodic table. So now we found the top term. We need now to find the bottom term, the liters of solution. Remember that this mass is associated with 1 milliliter. So how many liters equals 1.0000 milliliters? (1,000 milliliters equals 1 liter, so we have and finally we can find the molarity. Coming back up here and substituting because now we have both terms. Answering it to the right significant figures gives us 3.00 molar solution, or we can write it as 3.00 moles per liters. Either answer would be correct. Now let's calculate the molality of the solution. Molality is moles of solute, which is sulfuric acid, divided by the kilograms of the solvent, which in this case is H2O. Let's go back to this equation. Remember that 1.1783 is the mass of the solvent plus the solute. We already know that 25% of it is sulfuric acid, therefore 75% is water. So let's focus on calculating the kilograms of water. Let's start first with the grams of water. Out of 1.1783 grams, 0.750 of it belongs to water. And we're carrying 3 significant figures. Converting that to kilograms. Now backing up to substitute. Molality equals the moles of sulfuric acid divided by the kilograms of solvent. Let's back up a moment to find the moles of sulfuric acid. 3.003 times 10 to the minus 3. Notice that you don't want to use a rounded number. You want to use at least one digit beyond the last significant figure that you want to keep. If you keep more, that's okay, but you don't want to round it off yet. So this final calculation gives a 3.40 molal, or we can write it as 3.40 moles per kilogram. Either answer would be correct. And we have one calculation left. Mole fraction is part C. The mole fraction moles of solute over moles total, and the moles total of the solution would be the moles of sulfuric acid plus the moles of water. Out of these, we know this one. We just need to calculate moles of sulfuric acid and we'll be done. I'm sorry, did I say sulfuric acid? I meant moles of water is all we need to calculate. And we've got the mass of water on the previous slide, 0.88372. Don't forget to change moles to grams. You need the molar mass, which you calculate using the periodic table. Now we have everything we need. Plugging all the values into the equation. Moles of sulfuric acid, I have it on the previous slide, 3.003 times 10 to the minus 3. When we add the denominator, we're going to have moles on the bottom and moles on top, so we're going to end up without any units for a mole fraction. This final calculation is 0.05769, and we're carrying 3 significant figures. So this is our final answer. And again, notice that it is unitless. The next exercise is a quiz, and it's not a real formal quiz. It's just for you to determine if you're understanding how to solve these problems or not. This particular problem is asking you to determine the mole fraction, the parts per million, and the molality for the problem stated above. Go ahead and do it on your own, and at the very end of your chapter outline, you'll be able to find the answers for it. If you did it right, high five, you're understanding. If you didn't get all of it correct, then watch the video that's found in Blackboard right after this one, titled Calculating Concentration, Part 2. In this particular video, you won't be seeing me. You'll just see how the problem is set up and solved. And that way, you'll be able to find out what portion is giving you trouble. After watching that video, if you understand it, great. If you don't, come see me during my office hours. This is one of those important building blocks that you want to make sure you get well from the beginning. So, good luck. See you soon. Bye.